Yellowstone supervolcano diatoms. These fossilized oxygen-producing diatoms of hydrothermal deposits in Yellowstone. I've long wanted to do a video on this because of the tremendous amount of diatoms produced in Yellowstone hydrothermal areas. We know that there's over 10,000 hydrothermal areas in Yellowstone and over 60% of the world's geysers. Let's take a look at this short NASA video as to what diatoms do, how important they are to life on Earth. They give us about 0.5% of our oxygen that we need to live. A NASA video concerning diatoms. If we take 2 breaths, we have to know that one of the 2 breaths is due to the oxygen that diatoms give us.
Diatoms are one of the most abundant types of marine phytoplankton, but a new 15-year-long NASA study reveals global populations have declined. Diatoms, like all phytoplankton, have chlorophyll, the same photosynthesizing pigment as plants. They occupy the surface of the ocean where they harvest light from the sun. In large numbers, diatoms form colorful swirling blooms that can be seen from space. Scientists use NASA satellite data, water samples, and computer modeling to determine how diatom populations have varied. This data visualization shows changes from 1998 to 2012. According to the study, significant decreases in population, shown here in red, are mainly in the northern hemisphere. Scientists link this to a shift in the availability of nutrients.
Diatoms rely on nutrients such as nitrate, silicate, and iron to reach the surface layer where they live. What the study shows is that the availability of these nutrients has changed due to the way they cycle within the water column.
Diatoms occupy the surface area of the ocean called the mixed layer. Nutrients collect on the ocean floor and are cycled up to this layer. Various physical forces can cause the depth of the mixed layer to become shallower so that fewer nutrients reach the diatoms. Without these nutrients, their populations decline. This map shows areas on the globe where the depth of the mixed layer shallowed.
It's hard to pinpoint exactly why these changes have happened. Things like wind, circulation, and temperature can affect the way these nutrients are brought to the surface layer. We hope a longer study can yield more information on whether these changes are in fact a trend or variability.
So we see how important diatoms are to life on Earth. According to an abstract, scientific fossilized diatoms of siliceous hydrothermal deposits in Yellowstone National Park, the study of eukaryotic extremophiles, these are the types of life forms found in very hot, very toxic, very acidic or basic hydrothermal areas, is relatively novel, and therefore documentation of the structures and function of these microorganisms is continental hydrothermal systems globally is limited. In the study, they said they investigated fossil diatoms in the hydrothermal deposits of the Upper Geyser and Yellowstone Lake hydrothermal basins in Yellowstone National Park. As we know, Yellowstone Lake is over the caldera of Yellowstone. So they utilized preserved diatom assemblages to infer local environmental conditions. Siliceous sinter from both Upper Geyser Basin and Yellowstone Lake contains evidence of in situ diatom growth within these environments. At Upper Geyser Basin, the assemblage consists of species that could grow on moist siliceous sinter and was dominated by a type of diatom called Rhopalodia gibberula. Diatom values were found in various preservation states, ranging from nearly pristine to highly diagenetically altered. Diatoms collected from siliceous spires in Yellowstone Lake consisted largely of tecoplanktonic and benthic species and were almost certainly growing on the outside of the structure. With an assemblage indicative of relatively shallow alkaline waters, what remains unclear without access to material for high-resolution dating is whether diatoms colonized in spires during hydrothermal activity or after activity ceased. They said our results indicate that diatom frustules can, to some extent, survive alteration in low temperature, that is about 76 degrees Celsius, hydrothermal environments. And this is by Sabrina Brown, Cheryl Fritz, Lisa Morgan, diatom research. These are some examples of the diatoms found in Yellowstone. According to another study by Bio1 Complete, Edward Theriot, Cheryl Fritz, Kathy Whitlock, Daniel Conley, late Quaternary rapid morphological evolution of endemic diatoms in Yellowstone Lake, Wyoming. That Yellowstone Lake, as we said, is over the caldera of Yellowstone. The centric diatom Stephanodiscus yellowstonensis, this is the type of round diatom found in Yellowstone. Theriot and Stromer is endemic to Yellowstone Lake, where it can be an important component of the summer phytoplankton assemblage. Its close relative Stephanodiscus niagara, Ehrenberg, the abundant in nearby lakes and regional reservoirs. They said we used the stratigraphic record of Yellowstone Lake to investigate the evolution of Stephanodiscus niagara and Stephanodiscus yellowstonensis, and to describe the limnological, that is the lake, and climate conditions associated with the evolution of these diatoms. A dramatic morphological shift took place between about 13.7 and 10,000 Ka, but morphology remained stable from 10 Ka to the present. Coincident with morphological change is the Stephanodiscus niagara, Stephanodiscus yellowstonensis complex, where were changes in the diatom species assemblage, biogenetic silica concentration, sediment lithology, and regional vegetation. These changes suggest an environment that experienced progressive warming following the retreat of continental glaciers. So the diatoms were able to show the scientists the temperature changes of the area of Yellowstone as the glaciers retreated. They said we could not identify a specific selective factor driving evolution. Nevertheless, non-random morphological evolution strongly associated with continuous environmental change suggests that directional selection is a reasonable hypothesis to account for evolution of the Stephanodiscus yellowstonensis. Protists are presumed to evolve gradually after speciation events because of large population size, high dispersal capacity, and low reproductive barriers. But published diatom examples and the evolution of Stephanodiscus yellowstonensis suggest that it is premature to generalize about rates of evolution in protists, or at least to include diatoms in this generalization. Citation is Edward Theriot, Cheryl Fritz, Kathy Whittock, Daniel Conley, Lake Quaternary Rapid Morphological Evolution of Endemic Diatoms in Yellowstone Lake. So these diatoms are still to be found in there, and that's great news because even though these areas are very toxic, very acidic, or very basic, very hot, these diatoms are able to live there, and they produce, as we said, a lot of oxygen, just like phytoplankton. And our oceans as well give us a lot of oxygen. They're not only cooling the earth, but they're also giving us the water cycle, but also giving us oxygen. So I'll leave links below for you for this. This is one of the videos that I wanted to do for such a long time. The importance of Yellowstone in not only recycling water, but also heating up our atmosphere. If it wasn't for carbon dioxide that they release, we wouldn't have the temperate climate on Earth that we have today. But they also give us these lakes, these hydrothermal areas, give us diatoms that supply us with oxygen. Every 2 breaths we take, 1 is due to diatoms. Please leave your comments and thank you for your support. Please support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.